Hi, I'm Dor Atzmon, a PhD student at Ben-Gurion University. This research is called Multi-Directional Search. This is joint work with Zhao-Yang Li, Ariel Fellner, Eliran Nachmani, Shachaf Sperberg, Nathan Stuttervant, and Sven Koenig. In the multi-agent meeting problem, we have a map and k agents, each with a start location. The task is to find a meeting location for the agent. On the left side, the agents meet at location V1, and on the right side, the agents meet at location V2. In this research, we consider two cost functions to evaluate the quality of a meeting location with respect to the shortest path from each of the start locations to that meeting location. Sum of costs, which is the sum of the cost of the paths to the meeting location, and makespan, which is the cost of the longest path to the meeting location. In this example, we can see that V1 has lower sum of cost, while V2 has lower makespan. Multi-agent meeting has many real-life applications, such as choosing a gathering point for multiple traveling agents or suggesting a meeting location that needs to be close to important surrounding locations. To find the optimal meeting location for either sum of cost or makespan, we introduce MM star. MM star is a multi-directional heuristic best first search algorithm. While in classic heuristic search, the heuristic function estimates the cost to the goal location. Here, we cannot estimate this cost as we do not know where is the optimal meeting location. Thus, the heuristic function estimates the cost to the optimal meeting location plus the cost of the other agent to get to that location. We use this heuristic for minimizing either sum of cost or makespan, and we suggest three such admissible heuristic functions. I now briefly explain each of these heuristic functions. H1, the click heuristic, uses a classic heuristic such as a straight line heuristic between each two locations to compute a heuristic for the meeting location. H2, the median heuristic, is designed for grids. We compute the median location over both dimensions of the grid. This location is an optimal meeting location for an empty grid, and thus is admissible for grids with obstacles. H3, the fastmap heuristic, embeds the locations of the graph into a L1 space. Then, it applies H2 on the generated embedding. We proved formally that each of these heuristic functions is admissible, and that, given an admissible heuristic, MM star is guaranteed to return the optimal meeting location. We evaluated MM star with our heuristic functions and compared them to a blind search version of MM star. This table shows the average time of each of the different heuristic functions for 5 agents on 500 by 500 grids with 10% obstacles. Here, H2 was the fastest. We also experimented on a larger grid with many more obstacles called the Enigma. Here, H3 was the fastest. We showed that MM star always performs better with heuristics and explained the benefits of each of the suggested heuristic functions. The full paper of this research was accepted to ICHKA 2020. Thanks for listening.